And what kind of distribution is this? Is it a discrete distribution or a continuous distribution? So what is your x here? What type of x is this? Is this your discrete random variable or continuous random variable? It's a discrete. Okay. Why it is a discrete? It takes up values that we can make a list, right? So we can make a list. So here x takes up values like -2, 0, 1, 10. So we have this discrete random probability distribution. Okay. So this is what we had in chapter 4. And from this distribution, what did we calculate? Do you recall? So you were given a probability distribution. And what did we calculate from this distribution? What did we calculate from this distribution? What were the questions? You were given this distribution. It was the question. Now what were you asked to calculate from this distribution? We were asked to calculate. What did we calculate? We calculate mean, right? Which is mu. So we calculated mu, and we also call mu as the expected value of x, right? We calculated mu, which is mean. We also calculate variance, sigma square, right? We also calculate sigma from this distribution. So you were given a distribution and we calculate all of this. Okay, and we do have a formula to calculate this, but we are not calculating here. So this is what we had in chapter 4. In chapter 5, we talk about continuous probability distribution. And what did we use to represent continuous probability distribution? So for the discrete probability distribution, we have a table. We can use a histogram, or we can use a formula to represent discrete probability distribution. But for continuous probability distribution, what did we use in chapter 5? What picture we use very frequently? We had a curve, right? A smooth curve. So in chapter 5, we have this curve, bell-shaped curve. We don't need this. So we had this bell-shaped curve, okay, and we had x here, we had f of x, and this f of x is the equation for this curve, okay. Now here our x takes any number, okay, we don't know here, x takes any number here. And from this, what did we calculate in chapter 5? So you were given a continuous probability distribution, and what did we calculate? We calculate the probability of x, right? We calculate the probability. So here, let me call this is A, this is B. We calculated probability that x takes any number greater than A, less than B, and very similar. Okay, this is what we calculated. And what is this probability equals to from this graph? Is equals to area under the curve, right? So here we have this graph in between A and B. So we have this graph, this part of a graph in between A and B. And we calculate the area under this graph. So we need to find the area of this region. And area of this region is the probability that x takes a number greater than A and less than B. Okay? So this is, we calculated area. So this is what we had in our chapter 4 and chapter 5. Okay. Now, in this chapter 6, we have to, now in this chapter 6, you will not be given this probability distribution. We have to calculate, we have to find this distribution. Okay. We have to find this distribution. In chapter 4 and 5, you were given discrete probability distribution, you were given continuous probability distribution, and from that distribution we calculated mean, we calculated standard deviation, variance, and probability. Okay, now in this chapter our target is finding the probability distribution. So here in this chapter we'll try to create this table, we'll try to make a table for and we'll use this table to make an estimate of the population. Okay, now here, before we start that, let's start by defining a few terms here. So we have a parameter. Now this parameter is a numerical value, okay, that describes population. Okay, now can you tell me one numerical value that describe population? Population means a set of data. So you have a set of data. Okay, now what numerical value describe that set of data? What do we use? Like in chapter, I think in chapter 2, we had a different ways of describing population. Can you just recall one of the ways to describe population here? So what did we calculate from the set of data to describe a population? Mean, right? We calculate mean, and mean help us to describe. It does not describe in detail, but it does tell us that once you have a mean, we can know the average value of data, right? Similarly, we also had a median. So this mean, median are the numerical values that describe population. Okay? Now, so here, so we have a different, so the numerical values, for example, mean, okay, we did calculate mean of a population, we did calculate median, variance, standard deviation, okay, a binomial proportion or the binomial proportion, okay. So these are the numerical values: mean, median, variance, standard deviation, binomial proportion. These are the numerical values, and these values describe the population. Okay, for example, you have a population, you have a data set, and if you know the, okay, for example, the mean of that data set is 3. What can you tell about that data set? You don't know, you don't have the access of that data, okay? So you don't have the data, but you know the mean of that data is 3. Now, what kind of information can you get from that mean equals to 3? What kind of information can you gather? You don't know you haven't seen the data, okay? You don't have that data, but the only one thing that you know about the data is the mean of that data is 3. Now, from this mean equals to 3, what kind of information can you gather for that data? What can you say about the data if mean is equals to 3? Does the mean tells the half point of a data? For example, you have 1,000 data. Okay, you have a set of like 1,000 measurements. We don't know what measurements, we don't know those measurements, but we have 1,000 measurement. What we know is that the mean of that 1,000 measurement is 3. Now, what kind of information we can gather from that? Kayla, you want to add?
The mean is the
So mean is the average value, right? So you have a 1,000 measurement, and the average value of that 1,000 measurement is 3. We don't need to see that 1,000 measurement, but at least we can say this one, right? In the similar way, if you have a median like a 6, what can you say about that measurement? If the median is 6 for some data set, what can you say about that data set?
That is the average.
Mean is the average, but median is not the average. If median is 6, then that 6 is the middle point, right? That 6 is the middle point of that data set. Okay, now here all these mean, median, okay, let me take one more. Like for example, the standard deviation of 1,000 measurement is 1.5. What does that mean for you? What does it tell you?
That 3/4 of it, like how much will fall in between those lines. If it's one standard deviation away from the mean, it's going to be like close to 0 depending on which graph.
Okay, close enough. Sergio, you want to add?
Is it that over a long period of time?
Uh-huh.
That will be
That's the expected mean. Okay, that's the expected mean. Now, so for example, you have 1,000 measurements, and if the standard deviation of that measurement is 1.5, means the distance of each measurement from mean is around 1.5. Okay, it's not exactly 1.5 but close enough. Okay, now if you have a two data set, one data set has a standard deviation 1.5 and the second data set has a standard deviation 2.5. Which data set is more spread?
2.5.
The data set with a standard deviation 2.5 is more spread, right? So we use this kind of numerical values, mean, median, variance, standard deviation, binomial proportion, to describe our population. And these values, okay, these mean, median, variance, standard deviation, binomial proportion are called the parameter. So all mean is a parameter, median is a parameter, variance, standard deviation, all these are the parameter. Okay, now if we use a, now here we have a different symbol for these numerical values. Okay, if we are talking about the population, we use one type of symbol, and if we have a sample, we use a different notation here. Now what's the difference between population and a sample? Is it the same thing? What is the major difference between population and a sample?
Population is a whole thing, sample is a part of the population.
Okay, now, so if I take, so the students of, students of United States, that's a population. But students of this class is a sample. Okay, so population is always big, always a large, okay? And sample, it depends. It can be a 1, 2 or 3, okay? It depends. Now, if we have a population, okay, we all have seen this, okay? We use mu. I think we also talked about this in our previous chapter. So we use mu to denote mean of a population. We use eta, okay? This is eta, to represent the median of our population. We use sigma square to represent the variance of a population, sigma standard deviation of a population, and p for the binomial proportion for the population. Okay, and if we are talking about the sample, okay, x bar is a mean, but it's a mean of a sample. Okay, we have m for the median of a sample, s square variance for a sample, s standard deviation for a sample, and p hat for a binomial proportion for a sample. Okay, and this x bar, m, s square, s, p hat, we call this statistic. So statistic is a numerical descriptive measure of a sample, but parameter is a numerical descriptive measure of a population. Okay, so we have this mu, eta, sigma square, sigma, p. So these are the parameter. So we use parameter for the population. We have x bar, median m, s square, s, p hat for the sample, and we call this statistic. Now what is the major difference between population, between parameter and statistic? What is the difference here? So we have, okay, let me tell you. So these mu, eta, sigma square, sigma, p, these all are parameter. X bar, m, s square, s, p hat, all these are statistic. Now can you tell me the difference between these two? What is the key difference here? Okay, for example, so you have a mu, okay, let's consider the mu for mu is 2.7. Okay, so this is a height. Okay, 2.7. That's not a good number. 2.7 can't be height, right? Average height, let's take like 5.5, and x bar is 5.6. Now what differences do you find here? So what is the major difference here? So your mu is also mean, x bar is also mean, but you have a different value here. What is the difference here? Mu is 5.5, x bar is 5.6. Both of them are mean. That's the one common thing. But what is they are not same. They are not same. There is one difference. What is the difference here? They have a different value, okay, but that's not the difference I'm looking here. So what does mu tell us? Mu is the average of sample or population? Population. So this 5.5 is the average height of, okay, average height of people of United States. But that X bar, 5.6 is the average height of students of ENMU. Students of ENMU is the sample. Okay, population of United States is the population. So mu is, we use mu to describe population. We use X bar to describe a sample. Okay, in the similar way, we use sigma to describe the standard deviation of our population. We use S to describe the standard deviation of a sample. Okay, we use a parameter to describe population, to describe the large number. Okay, and we use statistic X bar M S square S P hat. We use this statistic to describe our sample. Okay, but they both mean the same. So mu is also mean, X bar is also mean, but we use mu for population. We use X bar for a sample. Okay, so here statistic refers to sample quantity, okay, sample, and parameter refers to population quantity. Statistic is for sample, parameter is for population. Okay, now, and in this chapter, as I said earlier, we will be using this statistic, okay, we will use this statistic. So we use X bar, median, S square, S, P hat. We will use this statistic to make an inference of this parameter. That's our goal. Okay, we will have a sample, we will have a mean of a sample, and with the help of that mean of a sample, we will estimate mean of a population. So we will make an estimate because population is large. Like for example, it's not impossible, but collecting or finding the average height of a population of United States, it's not an easy job, right? So we are big in number, but what we will do, we'll take one sample. Let's take a population of Port Ellis, and we'll use the mean height of these Port Ellis people to make an estimate of height of a US population. Okay, so we will be using statistic. Okay, we'll be using X bar or median, S square, S, or we might use all this statistic to make or to estimate parameter. That's our goal in chapter 6. In chapter 4 and 5, we already had that distribution. We just calculated the expected value. We calculated the standard deviation, right? But here, we have to use this sample statistic to estimate mu or median, sigma square, sigma or p. But so we will not estimate all, but we will estimate the mean of a population with the help of sample statistics, X bar, or sometime median. Okay, that's our target. So we are making an estimate. Okay, we are making an inference of population mean with the help of sample statistic. Okay, now here we have two different sample here. The first sample is that we roll a dice and keep a record of the number of dots that we get. Okay, so from this picture, so we throw a dice 3 times. Okay, so first time you see 2 dots, second time you also have 2 dots, and for the third time you have 6 dots. So you are rolling a dice for 3 times, and you are counting the number of dots that you see on a dice. Okay, so you throw a dice for 3 times. So you get 2, 2, 6. The order really does not matter. Okay, so you might get 6 at first, 2 second, and 2 third. It really doesn't matter. So we have this sample. Okay, so here we define our x to be. So we define x to be Okay, number of dots. Okay, so our x is number of dots. So we have this experiment of throwing a dice. Okay, and our x is a variable and x is the number of dots. So we throw 3 times, and first, so we, for this first sample we get, so our x takes a value, so x takes a value 2, 2 and 6. Okay, now do you now here, what does it mean by x equals to 6? What does it mean? So I have x equals to 2 to 6. What does it mean by x equals to 6? Or what does it mean by x equals to 2? We are throwing a dice and we are recording the number of dots in each throw. Okay, so x equals to 6 means you get 6 dots in one throw. In first, second or third, it really doesn't matter. So x equals to 2 means we get 2 dots. Okay, and 2 means that you get x equals to 2 dots. So this is our sample 1. Okay, in sample 2, x still represents the number of dots, but our x, so we get 3, we get 4, and we had 6. We had the same number of throw. Okay, we throw for 3 times. So you have a first sample, you throw it 3 times. You collect the number of dots. Okay, and once you have complete 3 throw, you again start a new sample, and your second sample has x values 3, 4, 6. Okay, are you clear about the experiment here? You throw a dice 3 times. Okay, you collect, you record the values, number of dots you get in each throw. Then you do second sample. Okay, now for each sample we calculate median and x bar. Now for the first sample, so what will be our median? So we have 2 to 6. What will be our median? 2, right? The middle value is 2. And what is our x bar? So how do we find x bar? 2 plus 2 plus 6 divided by 3, right? That's 410 divided by 3, which is it 3.3? Now let's find the median for second sample. What is our median? 4, right? And what is our x bar? 3 plus 4 plus 6, that's 9, 13 divided by 3. And what is that? 13, is it 4.33? Now why did I use m, x bar, not mu and eta? It's because it's a sample. Okay, so we are finding the mean of a sample, so we use x bar. We are finding the median of a sample, so we have our m. Okay, now here in this case we are given our mu for this experiment. Bless you. So the mu for this experiment is given as 3.5. So this is given to us. Okay, and what are we trying to do here? We are using our statistic. So what are the statistics here? So for this, what are the statistics we are using here? Who can tell me what statistic are we using here? What are the statistics are we using here? No, sample is not the statistic. What is the statistic? Let's go back to our table. So what are the statistic? These are your statistic. X bar is the statistic, m is the statistic, s square, s, p hat is the statistic. Now, can you tell me what are the statistic are we using here? What are the statistic are we using here? Okay, one more time. Okay. All these, okay, x bar, m, s square, s, p hat, all these are statistic. Okay, mu, eta, sigma square, sigma p, all these are parameter. Okay. Now, can you tell me what statistic did we use for sample 1 and sample 2? Isn't it median and a mean? See, we are using m, right? So we have m. Isn't median m a statistic? X bar is a statistic, M is a statistic, X bar is a statistic. But this mu is not a statistic. This is a parameter. Okay? So we are trying to find, we are trying to use this statistic to make an estimate of mu. We already know mu, but still we are trying to find the best statistic to make an estimate of mu. Now from here, what can you say? Our mu is 3.5. Okay, so in the sample 1, which one is very close? Is your median X bar which is close to mu? Which statistic is close to mu value? X bar is close, right? Your mu is 3.5, X bar is 3.3, median is 2. So X bar is close to our population mean from sample 1. From sample 2, so which one is closer? So your mean, population mean is 3.5. Your median for a statistic is 4, X bar is 4.33. And which one is out of median and X bar, which one is close to this mu value? So you have 4 and 4.33. So which one is close to 3.5? Is 4 close or 4.33 close to 3.5? So you are trying to find 4 is closer to 3.5 or 4.33 is closer to 3.5. Which one is close? Which one is very near to 3.5? Is 4 near to 3.5 or 4.33 near to 3.5? 4, right? So here our median is close to population mean. Now from these two samples, which one is the best estimator of population from according to sample 1? Which one is very close to our population mean? X bar is, right? X bar is good estimator for sample 1. For sample 2, which statistic is a good estimator of our mu? Median, because this 4 is very close to 3.5. So median is a good estimator for our population mean. Now, if we have a third sample, do we get, now here, from here, now if we have a third sample, for example, you have a third sample, sample 3, you roll a dice, you collect the number of dots. So for example, you had 1, you had 5, and you had, 2. So these are the number of dots in sample 3. Now let's find the mean. Our mean is 1 plus 5, 6 plus 2, 8. 8 divided by 3 is 2.6. And what is the median? What will be a median? 152. Median will be middle value. Which one is the middle value?
2.
Did you all forget to find the median here? Yes, 2 is, now here, out of this X bar and median, which one is very close to 3.5? 2.6 or 2? Which one is close to 3.5? X bar, right? So for our sample 3, X bar is close to mu. So from here, what we can conclude is that neither mean nor median is a good estimator. It means this information is not enough. We need more information to find the good estimator. We are trying to estimate parameter here. From the sample statistic, we are trying to estimate parameter. Now, do you have any question up to here? Now, next, let's define sampling distribution. Now, this sampling distribution, this is the collection of values and associated probabilities of each statistic. So we collect the values of each statistic and its corresponding probabilities. Now So like let me take this same example. So from these three example, so what are our statistic? So in these three sample, what statistic did we use? In these three sample, what statistic did we use?
X bar.
X bar and median, right? So we collect each values of X bar from each sample. So let me make, so we have X bar, and from first sample our X bar is 3.33, so its value is 3.3. okay, the next value of X bar is 4.33, and the last value of X bar is 2.6. So you collect all the values of this X bar, which is a statistic, okay, and its corresponding probabilities and associated probabilities, okay, which is P of X bar. So you find the probability that X bar is 3.33. We don't know 8, okay, so you will have this probability associated with each value of statistic, and this table is the sampling distribution. Okay, similarly, if you take median statistic, so what are the values median take in the sample 3? We have 3 different sample. From the first sample, median is 2. From the second sample, median is 4. From the third sample, median is 2, right? So we just need here. And now we find the probability that median is 2. Okay, we find the probability that median is 4. And this table is our sampling distribution. Now, what's the difference? We have seen distribution. So what's the difference between our discrete probability distribution? So we had X here. We had P of X. And X taking value 1, 2, 1/2, 1/2. Now this is our discrete probability distribution, okay? The first table is discrete probability distribution, but these two tables are sampling distribution. Now what is the difference here? They are not same, they look same, okay? Both are table, both has a values, both has the probabilities associated with each values, but what is the difference here? Kayla.
Instead of using X, they use X bar and mean.
Okay, in the first two table, we are using X bar and M, right? And what are X bar and M? What are X bar and M? These are the, what are X bar and M for a sample? Statistic, right? X bar is the mean of a sample, M is the median of a sample, and we call it a statistic. So we have the statistic used in first two table. We use X bar, we have M. But what about in the third table? We use X. Is X a statistic? What is X? X is just a discrete random variable. It's just any number. It's a number that our random variable assumes. X does not describe our data set. But X bar describe data set, right? Because X bar is the average value. Median describe data set. Median is the middle value. But X, it does not tell anything about the data set. Does it tell X is X? X does not tell anything about data set, okay? But whenever you have X bar 3.3, 3.3 is the average value. That's what we calculate here for sample 1. See, we have 3.3. Okay, so you should be able to identify whether your distribution is sampling distribution or discrete probability distribution. Okay. So in the sampling distribution, you have this statistic, okay? You don't have X. You have the statistic and their corresponding and their probabilities associated with each statistic value. Okay, you will have the probability here. You will have the probability here. And this kind of table is the sampling distribution. Okay. Now, do you have any question up to here? Okay. Now next here, now this picture. Okay, now who can tell me, is it a sampling distribution or not? Is this sampling distribution or continuous probability distribution? Now what make, okay, now it doesn't, okay, now what is the key here? What helps you to decide this is a sampling distribution?
X bar.
What helps you decide? What helps you decide this is a sampling distribution? You have this picture and you need to tell me whether it is a sampling distribution or a continuous probability distribution. A sampling, that's correct, but what is the reason? Like, how do you know that it is a sampling? It's because, what do we have here? X bar. So what we used to have for continuous probability distribution instead of X bar? We used to have X, right? Like when I start this chapter, so I think we had, see, here we had X. If we have a probability distribution, we are talking about this X. But now we don't have X here. We have X bar. Okay? And this helps to decide that this is a sampling distribution. This is not a continuous probability distribution, but this is a sampling probability distribution. Okay, now, so from this, so we already have the sampling distribution. And if you are asked to find probability that X bar, okay, X bar, I'm not using X bar, this X bar takes a number greater than 9, less than 11. How do we find this? The concept is same. If you have a continuous probability distribution, how did we find the probability? Probability is same as finding what? Area, right? So we use the same concept here. So we have a 9 here, we have 11 here. So that we want the graph from 9 to 11. So this is the graph in between 9 and 11. So the area under this curve is the probability. Okay? So we have this, so we find this area, and that area is the probability. Okay? Now you have this mu. This is a parameter. Again, we use this X bar to make an estimate of parameter mu. Okay, now we have this. Now it does tell us two sampling distribution. So we have a two different sampling distribution. So the red one, okay, the red curve, and this purple. Now what is the so what they are trying to, okay, now here it does not tell us what statistic they use here, but we have this two sampling distribution, okay. So we have a sampling distribution A, so this purple one is A, and statistic, the red one is sampling distribution for statistic B. Okay, now here the question for you is which one is, okay, what's the difference? Let's find the difference here. So we are trying to estimate sigma square, okay? Sigma square is a parameter. We had a mu parameter, but now we have a sigma square, and we are trying to estimate this sigma square with the help of this sampling distribution. Now in between these two sampling distribution, what is the difference here?
A is more narrow.
A is more narrow, okay. So what does it mean? A is more narrow means. What can we say about how spread they are, or is it less spread or more spread?
The variance may be smaller.
Variance gonna be smaller, right? So if we compare A and B, so our A is narrower, means we have data set in this region, okay, and our this B is wider. It means the variance is more, okay. For statistic B, our variance is more. It means more spread. In statistic B, it's very narrow. It means it is a less spread. Okay. And what about the next one? So this is our parameter. Now, is this parameter at the center of both distribution? So this sigma square parameter is it is at the center, not exactly, but very close to center for sampling distribution A, right? So if you consider this graph, our sigma square is at the center. But is this sigma square at the center for this red graph? No, right? So here, if we have a statistic with a less spread, and if the parameter is at the center, then we use those kind of statistic, those kind of sampling distribution to make an inference here. Okay, to find the correct statistic. So our target is, as I said earlier, we are trying to estimate parameter. We are trying to estimate mean of a population from a sample. Okay, and to find the correct sampling distribution, okay, to find the best sampling distribution, you're gonna pick a sampling distribution, okay, which has less variance, which is less spread and has a parameter centered. Okay, so out of A and B, which sampling distribution do we pick to make an estimate? Sampling distribution A. So we choose sampling distribution A, and we make an estimate of this sigma square. Okay, always we look for the sampling distribution with a less variable and with a mean or the parameter centered. Okay, let's do this much for today. Okay, we have a couple of examples here, and we'll continue this on our Wednesday's, not Wednesday, on Thursday's class.